Okay, welcome again. So we are looking at non-relativistic effective theories. So we looked at HQET, we looked at NRQED, and here today I think we'll discuss some more details about these theories. So first I'll start with some discussion about HQET. In particular, let's go into some nitty-gritty details. So we've looked at what HQET tells us about these heavy light systems, and one important use for HQET is calculating decay rates in these systems. So let me talk about currents and then decays. And then secondly, if I get time, I wanted to cover some aspects of the NRQED system that we talked about. So we saw that this is for a single heavy quark. These are for bound states of a heavy particle and its antiparticle. And one thing that we saw here was that if you wanted to look at these Coulomb exchanges, then you have to make a ladder sum in order to control your theory, because all higher order terms are of the same order as the lower order term. And this can be formalized by going from NRQED to a theory which is even lower scale in this, in the energy. Where you replace this ladder sum of Coulombic interaction by a potential. Okay, let's see how much we get to today. So this is roughly the plan. Okay, so we saw the implications of HQET on some masses, etc., of these heavy light systems. So, for example, you saw the implication of spin symmetry, which is a symmetry when the mass is very, very large compared to the scale of lambda QCD. And you saw the spin splitting is small. And in fact, you can also see that it's independent of the system that you're looking at. So you can talk about B mesons and D mesons, and you had some relations between the masses in these cases. So another important property that's studied using HQET in these systems is the decays, the weak decays, and these are related to currents in the theory. So we've looked at the Lagrangian so far, but we have not looked at currents in this theory. And let's look at what happens to this when we reduce from QCD to HQET. So for example, current in QCD will have the structure, let's say, gamma. So gamma could be gamma mu or gamma 5 gamma mu. And the reason to study these currents are, we know that, for example, processes like B2 pi, L nu, or some process like B2 D, L nu, they will be governed by these electroweak currents, right? So there's the electronic part, which I don't, which separates out, factorizes out, and then these currents in the hadronic section give you these decay rates. Okay, so just to make this discussion a little bit more concrete, let's look at a particular kind of vertex. So I have the usual Fermi interaction, which is so this is the CKM element. For example, B would go to a U here in this case. So there'll be a VBU. There's a leptonic part which tells you that L and U are connected by L bar 1 minus gamma 5 nu or its Hermitian conjugate. And then there is this current where you have some combination of gamma mu and gamma 5. So let's say that in some state that's on, so for example, a B state, I have the value of this current. So in fact, maybe just to use conventions, the definition that is used is u gamma mu gamma 5 u. Okay. So this is kind of standard. A current matrix element in a state will be given by some form factor f, right? And this, we can understand that this gives you the decay rate. So for example, a decay rate will be given in terms of this matrix element in like. So there are some base factors, but the key input that will go into this decay rate is this form factor. So now let's say, so this is standard material in QCD and standard model. The question is, can HQET tell us something about these? Okay, so let's look at this. So if I look at this matrix element here, so clearly it's going as P mu. And now I know that the velocity of this B is the same as the velocity of Q up to some small lambda QCD corrections. That is the chirality thing, chirality flip yeah. Let's see. Right. Yeah. So let me just say. So we've been calling this H, so let me call this HV. So I replace this Q field by my H field that we had introduced before. And I'm only considering electronic decay, yeah. Yes, this is the mass of the electron. Yes, okay. So I'm calculating a differential decay rate. So there'll be other decay modes also. Let me focus on this because you can cover a vast class of decays under this umbrella, right? All the electronic decays. This is 2. Yeah, exactly. Yeah. It is possible that m pi has been set to 0 to simplify this expression, but I mean, pion will be there, but no. No. B2. No, I think this will work, right? Because oh, right. I need a right. You're right. Yeah. Yeah. I need basically a pi here. So yeah, somehow this is just the decay constant. Yeah. Okay. This is. Okay. So, right. So here, now the only vector really in this problem is this velocity v. So then this becomes minus a v. Just a is some number for now. Now here, HQT starts to tell us some information. So let me look at the decay of B, the spin 0, and then let me look at the vector B measure. Okay. So now heavy quark symmetry tells me something. The point is that all the spin-dependent terms are small, 1 upon m suppressed. So really, the structure of both of them should be the same, except for this has a polarization epsilon mu. So this should go with epsilon. And this really is the only possible structure that you can have. So what this does is relate matrix elements of these currents for various states. But that's not all. If you have this matrix element for D instead of B, so let me not write it again. So B equals to D. Then in heavy quark symmetry, once again, MQ is infinite essentially, so then all these remain the same, except for the fact that the states are normalized differently in the two cases, right? This was normalized to be root MQ. Right? So the relation that we get is f of p is a by root mp. And same for d. So in fact, there is a nice relation that you can get, which is fb over ft equals to root m. And FB star, you can, for FB star is the inverse relation. So let's see how good that is. So if I look at the numbers, it turns out that FP or FD turns out. Sorry, can you put an FP star? That's the point. So heavy quark symmetry tells you that the difference between B and B star is the spin combination, right? And spin combinations are 1 upon n suppressed. If B star below. Yes. So I don't understand. Yeah, because yeah. But what is the definition of FB star? FB, right. FB star will be defined by this quantity. Yeah. Can you say that these two have a relationship and that's how? Exactly. Yeah, that's exactly. Right. And if you look at root MD by MB, this turns out to be 0. So not quite that great. So maybe HQT is not super quantitatively accurate, but let's not give up so quickly. There are, of course, things that are approximate here. Of course, we have made 1 upon MQ. This is leading order in 1 upon MQ. There can be corrections associated with this. This is also leading order in alpha S. So there could be corrections associated with that. What I want to cover today is look at this aspect. And this will just also give us some experience with matching and running of current operators in an EFT. So that's the goal. Okay. Before going there, let me just complete this story by introducing another set of currents that turns out to be useful. These are currents associated with heavy light currents, but you can have decays which are D to B, sorry, B to D. So similar story happens there. So let's say I have things like D. And this will again be governed by some form factors. Yeah, sorry, I'm okay. Right, that's right. So here again, you can have many kind of currents. D star, let me just call it B mu for now. B, and this will have another form factor. Let me not write this down. So this has D star, so there will be an epsilon. So there are many more combinations you can write. You can have A mu, B, and here, because it's axial, you can have, again, many other combinations. So I think this I'll give in notes. The point is that you get here six form factors. Okay. So now this, once again, looks complicated, but HQET actually simplifies things quite a bit. What you can show is that really all these in the leading order HQET are governed by just a single form factor or single function, which is, let's say, let me call it d bar. So once again, the only vector that you have in this problem now is velocity. Actually, I have two velocities, one for B and one for D, so V and V prime. And so all the form factors will connect to some functions of V. So I've introduced the symbol omega here. So omega is uh, so I think this will come from the exchange symmetry. So if I take the conjugate of this, I think, so yeah, if I just take the complex conjugate of this, I just exchange B with D, and in the heavy quark symmetry, if you ignore all the 1 upon MQ terms, then it should not change. So that's why it's a symmetrical. Yeah. 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 That will not survive, exactly. So the upshot is that all these combination D star, B, and D star, this is axial current, and D star. They all can be written in terms of a single function. So once again, this is a very good simplification. In fact, this function xi is quite famous. It's called the Isgur-Weiss function. And you can write your decay rates in terms of, okay. So I've not written. So this one that if you want, I'll write this explicitly. This actually is minus I omega. So the polarization comes in. And okay, since I'm writing everything, this okay. So now if I want to calculate these matrix elements, typically, well, if I do it on lattice, for example, the natural scale you do it is some scale of the order of GeV or so. But now the problem is here that if you are looking at scales, renormalization scales of about GeV, there's a separation between the mass of this B or C compared to this this lower scale that you want to look at. And therefore, there are large logs of MQ by mu. And that's Poirier perturbation theory. So, so the use of HQET is kind of twofold. One is it allows us to simplify things by using the heavy quark symmetry. The second thing it does, it allows us to resum these large logs in a nice fashion. So let's look at how that works out. Now, I'll just focus on the case of the heavy light system. So just some Q bar gamma Q, and see how the matching between HQET and QCD is done, and how you run down from a scale which is around mass of B to a lower scale. Let's take a specific current example, Q bar gamma Q. Okay, so this is the operator in QCD. And now I have to mash this to some operators. Okay, so now there are two vectors that can come in HQET, basically gamma mu and V mu. So naturally, this won't simply go to Q bar gamma mu Q. In principle, you can also get a contribution to Q bar V mu. So, so the matching is simply, let me call this V mu. So V mu is equals to Wilson coefficient Okay, so I've introduced many symbols here. So, but these are kind of familiar to you since you've looked at EFTs for some time now. So in HQET, of course, there are these operators Q bar V mu Q and Q bar gamma mu Q. And now these can have specific Wilson coefficients. And these Wilson coefficients will depend on both MQ and mu. And in fact, the way they'll appear is in terms of logs of MQ/2. We'll see this explicitly. And of course, it depends on the coupling also. Of course, at leading order, we know what happens. At leading order, basically, this is 1 plus order alpha S. Let me not call it Q, since it's a HQT field. So let's use the correct. And so now this this is actually kind of obvious. You have this operator, and in both the theories, I match them up. So at leading order, of course, I'll just get 1, and this will not be presented. Okay, so that makes sense. The molecule is the light. Right. So for now, I'll just focus on the light heavy current. And you can do exactly the same analysis for the heavy. The only thing is because there are 2 vectors there, it just becomes a little bit more complicated, but the idea exactly remains the same. Okay. So the question is, can we calculate these order alpha S coefficients? And that's kind of straightforward. So just you have to match certain quantity in QCD versus HQET. So the natural thing to match is you start from a heavy quark, you put a gamma here, and get it. So this will be in HQET. And QCD, the same idea. So let's choose the momenta. It's useful to choose the momenta so that this has a 0 momentum, and this. Right. So how will you match this? So let's do it this way. So how will you match the 2 theories? So if I look at this, write this explicitly in HQET, this will be U bar of MV mu, gamma, and Q of 0, 0. Like U of. Okay. And in QCD also, I'll get exactly the same thing, U bar MV mu. So, of course, I can simplify things because this is non-relativistic. So I can use the fact that some components are large, some components are small. But the thing is, in both, I'll be doing exactly the same thing. So there is no space for any other operator. So the matching is simply that at leading order, this simply matches to this. Is that okay? Yeah. Okay. So now the key point is that this doesn't hold true once you get to next to leading. So the diagrams that, so the one natural diagram that you will write, which is one loop, is you have some diagram of this kind. Okay, and this is gamma. Let me just be specific and use gamma equals to gamma mu. Other gammas work similarly. Okay. So, right. So let's say, so this is tree level. So let me look at what are the one loop contributions. So let me just draw the diagrams first, and then we'll see how things go. So of course, there's one diagram which is, as you'd expect, a vertex correction. I need some counter term to cancel infinities here, so that will appear. Then another thing that I'll need to do is that I'm calculating a matrix element here. So from LSC rule, I know that there'll be a factor of ZQ, root ZQ here, and root ZQ here. Once again, at tree level, ZQ is just 1, so it didn't matter. But now I'll have to take care of it, ZQ. Okay. Actually, the diagrams are the same in both the theories. The evaluation is different in the two theories. Because, for example, here, I know that in QCD, when I do DIMREG, the mass won't really play a role, and ZQ will be the same as this. But here, I've taken the heavy quark, I'm treating the heavy quarks separately, distinctly, so this turns out to be different. So in fact, yeah, so let me just write ZQ here itself, and right. Similarly, when I calculate this diagram, once again, the value will turn out to be different. Okay, so let me just yeah, I mean, I should have written it. I was a bit lazy. You'll have to add. Okay. So I think maybe it's not worth going to the details of the calculation. So you saw the main idea of the calculation when Abhishek did it in the last class. So there are two key technical aspects. So mainly this diagram is the new one that you have to calculate. All the rest you've calculated previously in your quantum field theory courses. This is really just the QED vertex renormalization, right? So when you calculate this, you have to use a slightly different technique because the propagator for the heavy quark is different from the light quark. And there was a new Feynman trick, Feynman prime trick that you have to use and calculate it. So beyond that, there is really nothing much. So what I'll do is give you the final answer. So what turns out to be true, what works out is, so m cube and mu alpha turns out to be equals to okay. So so let's look at the result a little bit and try to get some key features out. So the key feature that affects us is that you get a log of mq by mu here. So what this means, this is actually a concrete manifestation of what I said, that now if what you want to do is calculate some matrix element of this operator in a certain state. And now, of course, you'll have to renormalize it, and you'll have a renormalization scale. And now C is, of course, just a number. And if you take the renormalization scale to be MQ, then this log is small. So then that's good for you because you don't have large logs. But it becomes bad for you in the sense that now you have to calculate this matrix element at a scale which is MQ, where it's not even a bound state, right? So that's not a good choice. So what you want to do is somehow run these Wilson coefficients down to a lower scale at which you can calculate the matrix element more easily. Okay, so so matching does not solve the problem of running, but it just tells you what you need to, where you need to. Yes, yeah. That it doesn't have logs at this order, basically. And there might be a deep reason for it, but I don't know. Yeah. Running of alpha is the same as in normal QCD. Below the bottom mass. So you have to do a threshold matching at the bottom mass, and then you run it with 4 flavors. No. So this is QCD, so those are there. This. I mean, if you're worried about, there is one technical issue as to running in QCD depends on whether you're above the bottom, the number of active flavors. So you, at every threshold, you'll have to do a matching, but it's the same. Oh, you mean there's no TA here? Yeah, yeah. Yeah, yeah. 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 They don't appear in the matching, but they appear in the running of alpha. I think that's his question. Yeah. Yes. Yeah. No, no. At leading order, it will be exactly the same. Uh, yeah. Okay. You're saying I can replace. See, the thing is, no, no.
So if I think of bar gamma just Q by the tree level H, small hd and other stuff. So at leading order, I get hd bar gamma mu hd, right? One for bottom and one for
Exactly.
T, one for B, one for T. So then that looks like there's a term one in the gamma mu.
I think maybe what he's saying is that in this case, both can be, gamma mu itself can be replaced by V mu. Right. So we saw already, I just erased it. It's you can replace it by V mu as such directly, right? So there is no difference between uh, gamma mu and V mu as such. You don't need to consider two operators separately. Right. So uh, so now let's say, so this matching I will do at a scale which is order MQ uh, because uh, because then this log is small and I'm happy. And then I have to run down to a lower scale. So uh, once again, actually the diagram is still the same. So the main idea is that to run to a lower scale, I need the anomalous dimension of this. So, so I have this operator mu and mu. So this Abhishek introduced last time. Basically, I have a renormalization of the Q, renormalization of the capital Q, and the overall renormalization of the operator, and that gives me the counter term. So this is the renormalized operator, and this is the counter. Okay. So the upshot. So once again, you calculate these quantities. The diagram is actually turns out to be the same. And the upshot is that Z0 is equals to so if you want, you can write this. I can reduce. Okay, so if I expand in epsilon, and that will give me the running of Z0. So in fact, the anomalous dimension of Z0 is given by d by d log. And this is pi. So therefore, now I can run from a scale which is higher to a scale which is lower. The upshot being that so this is related to the QCD beta function, and this is the anomalous dimension that we compute. Hmm. Good. So they can't mix because of, I mean, they are different, they have different symmetries, but there is one thing. So for example, for the vector and the axial, there's a relation. So it turns out that for the axial, C2 is just the same quantity with a minus sign, and C1 is, so there are relations, but they don't mix. Like, just because the minus sign, I think you just get some minus sign because of amus, because of the gamma 5s, and that's why you get minus sign. Okay. That exactly right. You started with just gamma mu, and then you saw that both got generated. So obviously that's okay. So let me go to the bottom line here. Now let me calculate FB by FC. So A's are these functions that I introduced earlier. These are related to the form factors by the square root of m's. So now if I calculate this, So this was 0.89. This earlier was 0.5, 0.6 basically, 0.59. So this factor helps. This turns out to be of the order of 0.6. It helps a bit. It moves you in the direction of the result. So this result is from lattice QCD. So it moves you in that direction, but still does not get you the. So leading order in alpha S isn't enough. What you actually need is probably there are more effects associated with 1 upon MQ corrections. And clearly, charm mass is kind of on the borderline of being not too heavy. So, so we can expect these heavy correlations to break a little.
So the bottom quart mass, MS bar mass, and the capital B mass,
Yes,
they're not the same thing. Right?
they're not the same.
But when you are utilizing these relationships, like on HV side, the scaling goes as 1 over M sub small b, and in the heavy quarks, the one particle state goes like M capital B.
Yeah.
So naively, if you try to put, would that bring like additional powers of alpha S?
Powers of alpha S is, I don't understand. So there will be some lambda, some correction.
M capital B by M T should go as M small b by MC times some crap. The crap is some powers of alpha. Is that?
So yeah, you're saying.
No, MD.
Oh, you're saying plus
Times some crap.
Oh.
I mean, anything you write in plus, I can convert it in times. If I do that, then this would be bring out an additional PhD. We're talking about theory.
Yeah. So
there, the scaling you were cancelling in capital E with M small to get that. But you are using heavy quark, which is an expansion around M small. One particle state is expansion normalization around M capital. So there is little left.
Right. So you'll get some corrections of. I think there is sort of similar. So what I was thinking was that MC is not super large compared to lambda QCD. So here the correction. So it will be MB by MC. This will be 1 plus lambda QCD by MB. So this will be smaller.
Right. So no, but you see, lambda is alpha S ratios of, you think of alpha S like the QCD, the QCD scale and lambda, right? All fixed by
some alpha
coupling scale, and it's some alpha with some beta function to the power some dependence.
Right.
From the running.
Yeah.
Divided transmitted. So it looks like this is like a 1 plus alpha S to the power kind of a thing.
No, so I think the question, but I think it's still an important question. So what you are thinking is lambda is MC times some alpha S.
1 plus something like that.
Yeah.
Right?
So
1 plus complicated thing, but which you can always turn as some e to the power log of some crap. So that's what I mean. So it can write always the product way.
Yeah, but I think still if lambda QCD by MC is small.
Right. So in that alpha is also small.
I mean, it's like order, or you're saying this turns out to be above.
Alpha is over MD divided by alpha is over MD. This is 1 plus small.
Yes, right. Agree.
So this is also 1 plus small.
This is, yeah, right.
Maybe the coefficient is different.
I think the coefficient is different here, yeah.
Question from heavy quad to heavy laser connection. That he has taken.
Yeah, that I'll take it.
The scales are different. That's the reason you get that.
Yeah. So basically, this is happening because you're matching at different scales. That's all.
No, no,
Yeah. I understand. So this is order, let's say 1.2, and this could also be order 1.2. So one has to think about what this exactly. Yeah. Okay. So I think yeah. So I mean, I don't think it's maybe it's a good idea to sort of just pause for a second and just check that you understood the entire framework and ask me any questions if you want. I think I can talk for like about 5-10 minutes about this reduction from NRQED to PNRQED. But let me pause before I change gears to. Yeah, so you're right. I need a state here also. That's the main point. Okay, which state would I need? So, see, it will be, yeah, but then Q doesn't work out.
Match this gamma structure to chiral P. This is where you get U. The first term in U gives you 1, that gives you P decay constant. Second term in expansion gives you P to pi decay, so on. But that's one way to do that.
Yeah. So you just need a different matrix. How to calculate?
Yeah.
Oh.
That is one way. Catch this correct. It is also chiral symmetry that you build. Okay. Like it is a light quad that has SU3L plus SU3. You remember? Yeah. So you match this part with a U of pi. So that also has SU3L. Like that. It's in Manish one. So at U of pi as an expansion of 1 plus I pi.
But they both are, light. They are, both are the light.
Doesn't matter. You are trying to write an invariant term. U has an SU3L. There is a gamma, for example. The way you make it invariant, U has an SU3L. So you make this gamma a spurion that also has an SU3L transformation. Capital gamma. So put gamma mu gamma 5 as capital gamma. Right? Treat it as a spurion. Yes, it's a 3, 3 bar. So it's a identity under that. Now, if you try to write in terms of hadrons, gamma appears as you match the current. That has a 3 under SU3. So you need to put something else that also will match there. That's how U comes in. And this is where you are going to find that when you expand this U of pi, you are going to have 1 and pi. The 1 is going to give you
You don't get how to just
read the book
to
read the
light.
heavy light current.
Yeah, so basically you're saying something, introduce ions here.
Technically it doesn't work because the scale that you are transferring to the ion system is far above the type B. So imagine you are working in the phase space where all the momenta is gone into the electronic space and pi comes out almost static. So in that limit, you can use P to pi decay to map this property.
Oh, that is, no, I don't have that number. I think in 1 by MQ correction, I tried to look, it's a complicated calculation. Any other question? Okay, so no, what? Let me build up on something that Abhishek discussed last time, which was this idea that you've gotten an RQCD, which is at scale MV, but there is a specific set of photons in the theory, photon exchanges, which are slightly different in the sense that if you go to higher and higher orders, all these contribute in the same order. So these exchanges are of the order of mv square, and the question is, every time if you do a calculation in PNRQD and you have to resum this ladder, that becomes annoying. So is there something that you can do to simplify your life there? And the idea is that these exchanges of gluons, so these, the energies of these gluons, the energies of these gluons are of the order of mv square. So I always say gluons, but energies of these photons is order mv square, and these the momenta exchange are of the order of mv. And the reason is this, that you have an electron and a positron, which are separated by 1 r. So 1 upon r is of the order of mv. That gives you the momentum, while the binding energy in the system is of the order of mv square, as we discussed. Okay, so so if I start from my Lagrangian, right now, so actually before going further, let me make one change. Instead of working with these chi fields, let me work with chi c, defined as charge conjugation, which is basically the epsilon matrix times chi star. And the reason is that psi dagger created electrons, chi created E pluses. So, but this kind of is a bit antisymmetric. So, what I want to work with is chi star, which creates So that's just a small rewriting. There's nothing deep here. Let me just the only thing that does is make it more symmetric, except for the fact that the charge is negative. So let me call it D bar. So E of E plus is minus. Okay. So this is my bilinear part of the Lagrangian, and that's all we'll be interested in for now. There are higher dimensional terms, but we don't care for this discussion. Okay. Now, the idea is that, so this theory is valid at MV. Can I go to a theory which is where the dynamical degrees of freedom only have energies of the order of mv square rather than mv. And in that case, in particular, I'll have to integrate out these A0 modes. Well, of course, A0 modes which are MV, I'll have to integrate out. They are above this energy, but modes which are mv square mv, also I'll have to integrate out, because as you can see, these will have optionalness of the order of mv, so I'll have to integrate them out. And same for A vector. But these play a more important role, because as Abhishek showed, these exchanges are for the A0 photons. Okay, so so now how will this work? So I'll have to keep in mind, so the structure of this Lagrangian does not change. But now the point is that so far, at this point, I was allowing A0 to have these momenta. But from now on, I want to go to a theory which is a potential theory where A0 are not allowed to have this momenta. So how can I effect this? Well, I have to take into account the effect of these modes, and these terms don't change, but I'll have to add certain terms in order to match the results of this theory. And the natural operator to match now is the 4-point function once again. So let me not write the bilinear terms again. So they are same as so far. We'll have to massage them later, but so far they're the same. But the point is that earlier I had this vertex, which was E. And in this theory, so I've used the fact that K0 is 0, and this is just 1. So this is in another QED. In PNR QED, I don't have that diagram. So what do? I have to introduce a new operator, which is, let me call it the potential V. Okay. So V of K, the upshot is V of K is equals to E square, K square. Or if I write this in Fourier space, V of R is E square by R. There's a minus sign missing here. Yeah, okay, I am sad. Okay, I'll tell you why this. So I write it with the minus sign and I'll explain. So what does it mean for my theory? So this is a 4-point vertex. So this, I need four electron, 4 fermion operators to write this. So the upshot is that L is equals to bilinear terms minus d cubed R1, d cubed R2. Yeah. No, this is just yes. Minus I. Yeah, you're right. I think that's. So G00 minus I, let me call the full vertex, minus IV is this, minus I. So put K0 to 0. Then yeah, you're right. Right. So, yeah, so this is your A0 component, so that's why I put. Okay, so this is the upshot. Just to get matching between NRQED and NRQED, I need to have an extra term in my Lagrangian, which is of this guy. Okay, so that almost gets me all the way to NRQED. There's just one additional information that I need to use, which is that now there's a restriction that all the fields that appear in D0 and D vector have to have wavelengths which are of the order of mv square, mg square. So A nice way of putting in this restriction is actually now projecting this Lagrangian, this Lagrangian, onto a Hilbert space of the states that I know will be relevant. That is to say, kind of a state that we talked about before, something like d cube R1, d cube R2, by R1 minus R2, and side. So this is the wave function of the state, and these are the creation annihilation operators, and the only difference from before, I'm using IC. So if I project this Lagrangian onto this Hilbert space, then I get so let me define x r equals to x1 minus x2 and r equals to. Let me not try to copy it. Let me just call it a potential term minus. Okay. So this is just substitution. And so far, I've not done any approximation here. Now I can do an approximation because I know that I'm using the fact that these have scalings mv square, mv square, a0. So therefore, this quantity I can replace a0 x1 plus a0 x2 is of the order of r times del. So I can make a Taylor expansion here. And this turns out to be something that is familiar to you from your electrodynamics. This is the multipole expansion. I can go to higher orders in X, and they will be suppressed by more powers of V square. That's the key idea. So the final upshot is that after some simplification and redefinition, my Lagrangian looks like there's a redefined field S. Let me not go into that detail. Plus S R dot E. So just the usual kinetic terms. This is the center of mass motion, relative motion, del zero as expected. And finally, the multipole term, R dot E, and the potential term, which is of this kind, that V equals to minus E. So that gives you a reduction to the potential theory that you can use directly. And the main idea is that you can now solve the wave function, which is equivalent to resumming this ladder. That's all. Sorry for going over time, but I hope it was useful.
The references for EMR TV.
Yeah, that I'll, yeah, so,
Later and then
yeah. So I'll send the notes today.